Alright, time for number 7. So just a quick note, this is another case. The variables don't match on my PDF, but it should be fixed on the main one. So differentiate these three functions. So my first one is e to the b times cosine or cosecant of b. So a j of b is e to the b times cosecant of b. J prime of b then, by the product rule, is e to the b times derivative of cosecant, which is minus cosecant cotangent. And then plus the derivative of the first, which is going to be e to the b times the second. And now I'm going to go ahead and factor, because maybe I'm interested in zeros. It's good to factor when you can, as long as it's not too crazy. So both things have an e to the b. Both things have a cosecant. So what's left on the left part? I took away the e to the b and the cosecant. So I have a minus cotangent b. And then on the right side, I just have a 1. So again, I would do this if I were interested in finding zeros, which we very well could be. Now for part B, k of r is equal to 3 to the r log base 5 of r. So this is another problem where we need the chain rule, or not chain rule, where we need the product rule. But we have to be a little bit careful, because we've got 3 to the r log base 5 to the r. These aren't e's and logs, so we have to remember when we take derivatives what happens. So let's take a look. DDR, if I'm doing an exponential, then I get log of 3 times 3 to the r. That was the rule for taking derivatives of exponents. And then if I'm taking derivatives of logs with other bases, it's the opposite idea. DDR of log base 5 of r is equal to, and then we get 1 over natural log of 5 times r. So when you're taking a derivative of an exponent, you multiply by log of that number. When you're taking derivative of a log, you divide by the log of that exponent. Okay. So that in mind, k prime of r is first times derivative of the second, 3 to the r over log 5 times r, plus second times derivative of the first. So that's going to be log 3 times 3r times log base 5 of r. All right. And that is our final answer. We could simplify by multiplying this guy by log base 5 times r over itself. That way we would get a common denominator. But we're going to skip that step this time. All right, part C. L of x is equal to x to the x. So there are two ways to do this one, so I'll go ahead and do both. So way number one is L of x. By definition, x to the x is e to the x log x. So if I take a derivative, this is equal to, by chain rule, take the derivative of e to the something, so that's e to that thing, times d dx, x log x. And then this is e to the x log x. And then by product rule, we already did one like this. X log x, derivative of x log x is x over x equals 1 plus log of x. So in class, it was brought up, could we also do logarithmic differentiation on this one? And the answer is yes. So if I take the natural log of L of x, excuse me, I get natural log of get natural log of x to the x. And so I'm going to call L of x y, just to make this easier. Let y equal L of x. So putting that in there, I have natural log of y is, I have log of x to the x, so I can bring the x down. This is x log x. Hey, that's something that we've seen before. Take a derivative of both sides. Log of y becomes 1 over y, but y is a function of x, so we need to use the chain rule. So times y prime, that's the whole idea behind implicit differentiation. And this derivative here we've just done. This is 1 plus log of x. And I never did the last step on that one. But so y prime is equal to y times 1 plus log of x, which is equal to x to the x, 1 plus log x. And by the way, we use definition to get x to the x to be e to the x log x up top. So we can do the same thing up here and get the same answer. So two different ways of doing the same problem, but they both work out. All right, and that's it for number 7.